This experiment, as you know, is designed to allow us to understand the various techniques for measurements of flow rate. And it is a little bit lengthy experiment, but it is based on the idea that we will use different concepts to measure the flow rate. So I'm going to go over the device itself, the setup, and then we'll discuss how each one of these devices work. As I mentioned in my online lecture, we have 6 different devices. So I'll just go over those and then explain how you would do the measurements in here. So I'm going to start from where we have pressurized air coming from the system. We have 80 psi. We're going to start from there and show you the flow of air and how we can control it. So if you look here, generally, we have a valve that allows us to control the flow of pressurized air from the system. And this pressurized air is coming into this tube that is connected to a series of tubes. So if you come from the back here, we have so it will basically enter into the system through here, and then it will go through a very long PCV pipe that is instrumented along the way. So it starts from here. Okay, before I go to this point, the pressure here is obtained with a Bordeaux type test gauge, as you can see, where we can read off the pressure immediately right there. And then once the air is allowed in the system, the first device it will see is a sonic nozzle. And the sonic nozzle, if you kind of zoom in, you would notice that I have a cone, and the cone angle here is about 8.8 degrees. And then I can push that cone against a fixed area in here. And as I push it against the fixed area, I will constrict it. So I can actually allow, I can constrict it more or open it more, as we'll see in a minute. So with the micrometer, the height of that constriction, the height of the cone, is related to the diameter that I'm controlling. And that is also, I have a transducer that is also measuring the voltage that can give us information on the cross-sectional area right there. And then this goes into, continues on in series to flow through this rotometer, and the rotometer is graduated linearly, as I mentioned in my lecture, from 0 to 100%. And when it's 100%, you get 19.7 or 0.8 cubic foot per minute. So this is kind of calibrated by the manufacturer. And we have the temperature also measured. So this is a thermometer. It's connected to the rotometer, the base, that can give us the temperature of the air, because we're going to use standard equations for them. We're going to use standard equations related to the mass, the air, and its conditions as an ideal gas to make correction for the temperature and the pressure here on the rotometer. As the air goes through, then it will continue down here where it will go through a turbine flow meter. So if we can zoom in here, the turbine flow meter, the PCV pipe is sectioned, and the flow meter is connected to the sections where the turbine is inside. So as it rotates, it will induce an electromagnetic pulse at every rotation that can be measured. So this is kind of measures the frequency of each pulse. And the frequency, you can read it off here. So it gives you how many rotations per second of that wheel here that is moving. And then as we clear that turbine flow meter, you'll notice that I have a pressure point P2, which can be measured by the head of water. And that is I have switches here, RP1, RP2, RP3, RP4. These are reference pressures for the downstream, for the upstream inlet at different devices. So the upstream P2 is right here. And as we move on, we'll see the other points in the system. So going through here, continues on. Then now I have an orifice plate. And the orifice plate, the pressure upstream is P1. So this is RP1 right there. And the downstream, you got 1 point here, and then 2 and 3 and 4 and 5 and 6. Each one of these 6 is connected to a manometer, and the manometer is given here. So we have 1, 2, 3, 4, 5, 6. So these 6 points here are connected to the orifice plate. Similarly, if we just continue on, we'll continue on here. We will see in the bottom, we see in the bottom, this one here. Okay, I forgot to tell you before I exit here. On the way, I also have a laminar flow meter. A laminar flow meter, the pressure drop is linearly proportional to the flow rate. So you will convert the head of the head measurements here on the laminar flow meter to a pressure drop. So that will be another one of these devices. This is the 5th device. The 6th and most important device is down on the bottom, and that is before the exit. And this device is called the Venturi meter. And the Venturi meter, if you come closer, then you will see that I have, this is RP4. So this is the reference pressure, and the reference pressure is before. And then I have now 6 points, 1, 2, 3, 4, 5, 6. And these points here, I can measure the head in each tube by the manometer bank that I see right here. This is a Venturi bank. So you have 1, 2, 3, 4, 5, 6. So these 6, the height of these, of the water, which will be colored water, will be related to the pressure at each one of these locations. So as you can see that I have a conversion part of the nozzle and a diversion part, very, very slim conversion diversion, so I don't lose a lot of pressure. And then we're going to use this as the reference condition for the discharge coefficient as we discussed in our lecture. So now let's see how it works. Basically, if the air pressure is not introduced in the system, you have to turn this handle to allow system pressure come in, but it's already turned to flow because it's pointing horizontal. It means that I have flow already. And then I check the pressure here, 15 psi. And then I can control, because the flow is in series, I can control the entire flow by one single obstruction. And the single obstruction is going to be the sonic nozzle. So if it's completely closed here, and I would like to caution you not to tighten it too much, because if you tighten too much, you can actually damage the seating between the cone and the cross-sectional area, and that damage is plastic deformation we cannot recover, so it can introduce error in your measurement. So you have to be careful not to tighten it very much. Then now we can open it. As you open it, then there is flow already, and right now you have oscillations in the flow going up and down because it's very low rate and it's discontinuous, so it releases the pressure and it goes discontinuous. And then as I open the area more and more, I can allow for higher and higher flow rates. For example, I'm now up to 20% flow rate for the rotometer because I'm reading at 20%. And if I read now the flow meter, the turbine flow meter is giving me the number of turns per second, which is about 57 to 60. So it's not very stable, but if you go to higher flow rates, it will be more stable for the RPM of that wheel. And I can also measure the voltage related to the micrometer here and the temperature. And as you come closer to here, this is the tube bank for the orifice plate, and you will see that there's a pressure drop as you go across. There's also a pressure drop for the venturi, and these you will read off the graduations here because this is given in inch. So you have to read it off the height given in inches here. Let's try for higher flow rate. Let's go to, let's say, 50% flow rate. Then you will see substantial change in the behavior. Very nice distribution, pressure drop on the orifice plate and also on the venturi that you can easily measure in here. And same thing that you have very stable readings for the turbine flow meter and so forth. So with that, I think you'll be ready to do your experiments.